Alright, so what we're going to do in this video is prove that for all elements V in a vector space V, the equality 0V equals 0 holds. And to be completely clear here, the 0 on the left hand side and this 0 on the right hand side are completely different. They are not the same thing. They're not the same quantity. They don't they don't represent the same thing at all. So we just happen to use the same symbol for them because it's convenient, but they are different things, and we're going to talk about what they are. So I'm assuming you know what a vector space is, if you're studying linear algebra, and that is perhaps why you're watching this video, and hopefully you're studying a more proof-based course on linear algebra. And yeah, I am going to make another video on what a vector space is, where I'll explain in depth what a vector space is, and what a field is, and what a vector space defined over a field means, and explore all the properties and all the axioms of vector spaces. But for now, I'm going to assume familiarity with the idea. So in this problem, we're asked to show that the vector, which is 0 times v. Here 0 on the left hand side is a scalar, so it's a member of F, where F is the field that V is defined over. So vector space V, vector spaces are always defined over fields, and here I'm assuming it's defined over field F, and 0 is a scalar, it's a member of that field, and V is any vector, so any vector from the vector space V. So this is in V. So the scalar multiplication of 0 with v is equal to the vector 0, where z is a vector in v. So notice that this 0 is a scalar. It's a member of the field. So if the field in the consideration was the real numbers, it will be the real number 0, 0 on the real line. Whereas if this was the 0 on the right is what we call the 0 vector, or it's essentially it is what we call the additive identity of the vector space. So I do have the definition of the vector space down here. It's taken directly from Wikipedia. So if you notice, one of the axioms of the uh, vector spaces, there exists an identity element of in a vector space, and this identity element is what we denote by the symbol 0. It just happens to be the same with the as the symbol 0 that we use for the additive identity of the real numbers. So they serve similar purposes in their own domains, but they are not the same quantity by any means. So 0 is the 0 vector. So it's defined to be such an element, and it exists in every vector space. Without 0, there cannot be a vector space. In fact, that is that is the reason um, vector spaces over here. Um, where is this thing? Vector spaces are non-empty. It should be somewhere. I'm not able to find it. Yeah, a non-empty set. Wasn't able to find it. So the reason vector spaces are non-empty is because they have to contain the additive identity at minimum. So anyway, there exists an element 0 in V. Call the 0 vector such that V plus 0 is equal to V for all V and V. And because addition on vector spaces is commutative by, in fact, this property, this axiom above here, we should also have 0 plus V is equal to V plus 0 is equal to V for every single element or every single vector in V in the vector space V. Anyway, so now that we know what both of the zeros represent, let's start to prove this. So let's go proceed with the proof. I'm going to suppose that V is any vector in V. Then we have writing the proof a bit formally here to give you an idea of how generally you could go about writing this proof. Of course, you could have a completely uh, uh, a different but completely valid way of writing this proof, and so proof writing is a bit of maybe a bit of a subjective thing, but it's good to have an idea of how to like phrase proofs like this. So anyway, um, suppose v is any vector in V, then we have 0 times V is equal to, so I want to show that 0 times V is equal to 0. So why don't we just start with the LHS over here and see what we can get at here. One thing would be we're able to do some manipulations, so we get some quantity here. Let's say quantity q, and then oh, I shouldn't use the word quantity. That's probably not apt for this context. So I get some expression here. Let's call it e, and e1, and then that is equal to some other expression e2. That is equal to some other expression e3, and I keep going until I get what I want, which is the RHS, which happens to be in this case 0. Uh, and that may not be the case. Spoiler alert, in this problem, it won't be. But many times it is. So that's a pretty straightforward proof by equality, essentially, or proof by calculation, as it's also called. As I think proof by calculation is the correct term. And I'm not sure if proof by equality is even a term, but anyway. Um, yeah, in this problem that won't be the case, which we'll get into right now. But since we're trying to prove the 0 is equal to v, it's a good idea to just start with 0v and see what that equals. So if we really start with this, we don't really know what to do with this immediately. You may say, okay, v is any arbitrary vector. So this v, capital V is the vector space. This v is any possible vector in this vector space. So I have no idea what next to do with it. What do I write it as? Like I'm like not certain of what we can do with this. What I do know, however, is that 0 is the additive identity of the real numbers, and we know that 0 can be written as well 0 plus 0. So in fact, every element x of R, every real number x can be written as x is equal to x plus 0, and that even applies for the real number 0 itself. So 0 can also be written as 0 plus 0, where x is replaced by 0 here. So we write 0 plus 0, and the reason we do that will be clear in a second. So we have this is equal to 0 plus 0 times v, where 0 plus 0 is the same as a scalar 0. And now we'll use this property of the vector space, which we call no, sorry, not this property, the second property, distributivity of scalar multiplication with respect to field addition. So if you have if we have a scalar like a plus b, and this multiplying it by vector v, this is equal to av plus bv. So this is an axiom. So we're going to apply it above, and we have this is equal to 0v plus 0v. Great. 0v plus 0v. So far we have that 0v is equal to 0v plus 0v. So what we wanted is 0v is equal to 0 on the RHS, but we got an even longer expression. So clearly this is not something that you can, or maybe not clearly. I don't know if there's another way to approach the proof from here. I'm just gonna approach this proof the way that I've thought of. So, or at least that I've been exposed to when I was learning about linear algebra. And when I was learning about this topic in linear algebra, I mean, and so this we know now that 0v is equal to 0v plus 0v. So now we can use this. So now we know that there exists. So first, let's look at the property of inverse elements of vector addition. So for every vector v in the vector space v, there exists an element negative v, which we call negative v. If you wanted to be more abstract about this, you could say for all v in capital V, there exists w in capital V such that their sum v plus w, which is really the addition function, addition binary operation, their sum v plus w is equal to the additive identity 0, where 0 is the vector 0. And we typically think of because every single element has this and it always sums up to 0, we chose a special symbol, and the choice of symbols doesn't matter. You could replace v with x here, you could replace w with y, but for the sake of convenience, we're going to choose a nice symbol for w. We're going to call that v preceded by a negative sign. So that is v preceded by negative sign is what we call negative v. So v plus negative v is defined to be equal to 0. In fact, this is where the definition of subtraction comes from. Not sure if we really think of subtraction on vector spaces, but at least on in the context of real numbers, we have this property that for every x in R, there exists negative x in R such that x plus negative x is equal to 0, and subtraction of any two numbers a and b is defined to be a plus the additive inverse of b. So anyway, that's a bit of a detour. So we have that V is a vector and negative V is its additive inverse. So clearly every vector in V, every vector in the vector space capital V has an additive inverse. So because um, lambda V is also a vector by because of scalar multiplication, where lambda is any scalar, then we clearly know that 0v is also a vector in V, and therefore by that axiom, by the axiom about inverse additive inverse, it also has a well, an additive inverse. Kind of fumbled a bit there, apologies. Now we know that there exists negative 0v is what we're going to call this in V, such that 0v plus negative of 0v is equal to the 0 vector. So we have, uh, let me write that a bit formally. So I'm going to write it right next to it as the next sentence. So we have 0. I'm going to start with 0 and you'll see why in a second. I'm going to start with the right hand side here. So 0 is equal to 0v plus negative of 0v. And this is equal to 0v, and we know 0v can be written as 0v plus 0v from the thing that we showed above. So 0v is 0v plus 0v, and this is plus negative of 0v. And now we know that associative property is a thing. The associative property is a thing on vector spaces. So we can replace this with, we can change the order of addition, and we can say this is equal to 0v plus the addition of 0v plus negative 0v. And let me put that in parentheses for a bit more clarity. Maybe it's getting a bit cluttered, but really all you need to remember is that we've defined this little term, not it's not really little, but this term here to be the additive inverse of this term. So we know that this term is such that when we add these two things together, they give you 0, the vector 0. So this is immediately going to tell us that this is equal to 0v plus 0. Now the additive identity is such an element. 0 here is obviously the additive identity. So it's such an element which when added to any other vector in V, it gives you that same vector. So this immediately tells us is equal to 0v. So if you now notice carefully, we started with 0 and through a chain of equalities, we ended up at 0v. In fact, if you really notice above, this is exactly the thing that we wanted to prove. We started from the RHS, used a property that we figured out on the way, or like a hypothesis that we figured out on the way, you could say, and use that along with other known properties and axioms of the vector spaces to arrive at the left hand side. So we have proved what was desired. So that we can say is the end of the proof. It's not really a nice box. Proofs, when written formally, are typically ended with a nice box like this when you see them in a formatter like LaTeX. Anyway, that's the end of the proof.